Good morning. I continue with periodic trends. The first property today is electron gain enthalpy. Whenever a neutral atom accepts an electron and forms a negatively charged species, some energy changes are involved, and this energy change is called the electron gain enthalpy. Depending upon the element, the process can either be exothermic or endothermic. Usually, halogens or elements of group 17 have very high negative values for electron gain enthalpy because they need only one electron to attain the stable arrangement. However, noble gases or elements of group 18 have strong positive values for electron gain enthalpy because if they try to accept an electron and form a negatively charged species, they have to create a new shell. Their outermost configuration is already stable. Now, the trend. As we go from left to right, the value of the electron gain enthalpy becomes more and more negative, whereas as we go from top to bottom, the value becomes less and less negative. This is because electron gain enthalpy is related to the atomic size. As we go from left to right, atomic size decreases and force of attraction by the nucleus for the outermost electron goes on increasing. Similarly, when we go from top to bottom, the atomic size increases and the force of attraction of the nucleus for the outermost electron goes on decreasing. Next property, electronegativity. Tendency of an atom to attract shared electron pairs towards itself is called electronegativity. It is not a measurable quantity. However, there are many scales which are used to assess electronegativity. One of such scale is called the Pauling scale. According to this scale, the most electronegative element in the periodic table is fluorine. Now, the trend. As we go from top to bottom, electronegativity decreases, and as we go from left to right, electronegativity increases. This electronegativity can also be compared to the metallic and non-metallic character of the elements. That is, electronegativity is directly related to the non-metallic property of the element and inversely related to the metallic property of the element. Next property, valency or oxidation state. This property is understood in terms of the electronic configuration. Valency is same throughout the group. This property is useful in predicting the formula of compounds formed by elements. I will show you an example. If there are two elements, silicon and bromine, and I want to find out the formula of the compound formed as a result of combination of silicon and bromine. Silicon belongs to group 14 having valency 4 and bromine belonging to group 17 having valency 1. Thus the formula of the compound will be SiBr4. Last property, chemical reactivity. Atomic and ionic radii, as we know, generally decreases in a period from left to right. Ionization enthalpy generally increases and electron gain enthalpy becomes more negative across the period. The ionization enthalpy of the extreme left element in the period is the least and the electron gain enthalpy of the element on the extreme right is the highest negative. This results into high chemical reactivity at the two extremes and lowest at the center. This property can be related with the reducing and oxidizing behavior of the element. It can be directly related to the metallic and non-metallic character of the element. Thus, the metallic character of an element which is highest at the extreme left and decreases as we go from left to right, and the non-metallic character increases while moving from left to right across the period. Thus, chemical reactivity is more at the extremes of the periodic table and it becomes less as we come towards the center. I now wind up with anomalous property of elements belonging in the second period. Elements in the second period show properties different from the rest of the elements in the group because of the following reasons. The reasons are small size, high ionization enthalpy, high electronegativity and absence of d orbitals. Another anomalous behavior of second period elements. Lithium belongs to group 1 and the element below lithium is sodium. So definitely there is group wise similarity. But lithium also shows similarity with magnesium, which happens to be the element present in the next group in the next period of the element. Similarly, beryllium is similar to magnesium due to group similarity. But it also shows similarity with aluminium. This type of relationship is called diagonal relation.